All right, welcome back. Today we're going to finish up chapter 2. We were working with naming simple compounds. We're going to finish that up. And so you see we're starting with ionic compounds with polyatomic ions. So your polyatomic ions, they're what they sound like. They're going to be collections of atoms that form a single ion. Like for example, the sulfate ion. So you see you have like sulfur and oxygen. Um, Here you have the acetate ion. So you see that these are going to be multiple atoms that come together to form a single ion. And you want to make sure you don't get confused when you have these in a molecule, because even though these polyatomic ions have covalent bonds, which we'll talk about in a minute, covalent bonds in the ion itself, because they have a charge and they pair with another ion that has an opposite charge, they neutralize because it's the pairing of different ions with opposite charges. They still make ionic compounds. So as you see here down at the bottom, you have your sodium ion at a +1. So let's see here. You have your acetate ion at a -1. So you see that the +1 and the -1 come together to form a zero or a neutral compound, which is your sodium acetate. So just like naming other ionic compounds, you're going to do the name of your cation, name of your anion. So you're going to need to really just start in learning uh, you're going to have to just start in on learning these polyatomic ions. There's really not a, a set system to go about it. Some people just memorize them. Some people come up with their own systems. Some people use flashcards, but you're going to have to learn their formulas and their charges. So, here across the top, you see a number of your polyatomic ions, like your hydroxide, your OH negative, your oxalate ion, which is C2O4 with a -2 charge, your perchlorate ion, your ClO4 with a -1 charge, your phosphate ion, your PO4 3 minus with a -3 charge, sulfate, SO4 with a -2. So you just really want to start in on memorizing and getting down these polyatomic ions and their charges, because that's how you're going to, those charges are really how you're going to make your compounds. You have several, if you check the Canvas page, I put up a nice list of polyatomic ions to help you start learning. There are several on there where you have positively charged or cation polyatomic ions. Um, the only one I really want you worried about right now is ammonium. So your NH4 with a +1 charge. There are like two more on there, but uh, polyatomic cations are not extremely common. So let's really start by worrying about ammonium. And then one thing I wanted to point out is you have a couple on there. So you see here, you have thiocyanate and thiosulfate. Notice how they both have sulfur in them. So in chemistry, when you see that prefix thio, you're usually going to have a compound that has sulfur as one of the main atoms. So thio tells you this is a sulfur compound. I just wanted to point that out because it shows up everywhere as not a lot of people mention it. Now, one thing I always like to learn is that polyatomic ions come in families. Several of them do, especially your oxoanions. Oxoanions is going to be the more IUPAC way of saying that word. Some textbooks will call them oxyanions. It's the same word. I usually go with oxo because it's the IUPAC International Convention. But here's the thing. If you understand how these oxoanion families work and you understand the naming scheme, if you just remember one of the ions, then you have all of them. So here, you look at the chlorate family. So notice the naming scheme. First off, let's look at that. You have hypoite, ite, ate, and perate with your for your chlorine, your chlor as your base word. So you have hypochlorite, chlorite, chlorate, perchlorate. And the way this works is they change by one oxygen each time. So here, there's one oxygen. You go from hypochlorite to chlorite by adding an oxygen, chlorite to chlorate by adding an oxygen, chlorate to perchlorate by adding an oxygen. And then notice all of them have the same charge. So that's how oxoanions families work. So it's like if I know chlorate, I remember, oh my God, that's ClO3 with a -1 charge. But you're sitting there on an exam or an assignment or something, you go, well, what's chlorite? Oh, well, it's the same charge. You just got to remove an oxygen. So you might want to take a look at these oxoanion families and remember how they work. So here, your phosphite and phosphate. So you go from ITE to ATE as your ending by adding an oxygen. And of course, they have the same -3 charge. Again, bromite to bromate, ITE to ATE by adding one oxygen, and they both have a -1 charge. And here's another full family, your hypoiodite, iodite, iodate, and periodate. And so keep it, make sure you're noticing that you get the prefixes uh, at the extremes of the family. You have two ites and then two eights, and then you have hypo and per as your least number of oxygens for hypo, your most number of oxygens for per. And again, they just go up one oxygen, two, three, four. All of them have a -1 charge. So sometimes knowing the oxoanion family structure can help you figure out other ions if you just happen to remember one of the ions, like chromate or chlorate or nitrate, or uh, so it's like, oh, I have nitrate. Great, but I need a compound that uses nitrite. I didn't memorize nitrite. Well, wait, this is nitrate. You have that AT ending. I can go to nitrite by taking off one oxygen, and it still has a -1 charge. So I can figure that out using the oxoanion family. So let's start by looking at naming some simple compounds. Like I said, you're going to want to do your cation first in the name, anion second, like we've been doing. The thing you're going to want to practice is recognizing when a polyatomic ion is present. So here, your first one. So what are the ions we have? So I notice ESO4, the sulfate polyatomic ion. Okay, well, the magnesium ion, well, that comes from the periodic table. And I know from the fact that it is in column 2, the position of magnesium on the periodic table, that its ion will be a 2 plus. And then I remember that sulfate has a 2 minus. That's my polyatomic ion. The name here, magnesium, the cation, sulfate. Once you notice that you have a polyatomic ion in your ionic compound, the naming goes pretty quick. So if you look here, AlPO3. Okay, well, I remember aluminum is going to be a common charge ion at a +3. PO3, that's phosphite at a 3 minus. So again, +3 and -3, they're going to go together in a 1-to-1 ratio. And I'm going to end up with aluminum. Phosphite. The next one, the NH4Cl, this time I'm using the polyatomic cation. I know it's my ammonium cation. And I remember, oh, well, that's NH4 plus chloride. Chlorine is a group 17 element. So your group 17 elements take on a -1 charge. So again, 1-to-1 ratio, because we have a +1 and a -1. And this one, ammonium chloride. And here again, we noticed our hydroxide, polyatomic ion, potassium. Okay, well, potassium is in column 1 on the periodic table, and from what we've been studying, we know that column 1 ions take a charge of +1. I know that hydroxide is a -1 because I've learned hydroxide. And I get potassium hydroxide. While you're working on these, you might want to have your list of polyatomic ions out so you can figure this out, but you're going to want to make sure you know names, formulas, and charges of your polyatomic ions. Let's see. So we also, like we were doing before, we'll come across situations where we have to use subscripts to make sure we form a neutral compound. So uh, let's just start by looking at one that we were working on above. So this is so magnesium chloride. Okay, well, from the periodic table, I know magnesium is a 2+, it's in column 2. Chloride is a -1. Okay, well, these two ions, I have a +2 and a -1. Well, this needs to be neutral. Fine, I have 2, and so I'm going to do -1. I'm going to do -1 again. That gets me 0. So that's magnesium, chloride, and chloride. And so that tells me I have to have 2 chlorides to the 1 magnesium, and that would be my formula. But we can also do this with polyatomic ions. So let's look at magnesium hydroxide. We know magnesium is a 2+, hydroxide is a minus. So again, we're going to have to do our 2. There's 1 hydroxide, there's 2 hydroxides. These 2 here are hydroxides. Now, the way we do this is we use parentheses. So we have to put a subscript on the entire polyatomic ion. So parentheses, okay, I got my notes out of order there. I'm going to figure it out. Okay, so you have your magnesium, but you need 2 hydroxides. So the hydroxide is going to have to go in parentheses, and then I put the 2 on the outside. So now I have 2 of the hydroxides. So here's one, iron 3 nitrite. Okay, well, iron 3, great. So the Roman numeral helps us out. That tells us automatically that the iron has a +3 charge. Fe is iron, that's 3 plus. What is nitrite? Okay, well, I remember what nitrate is. That's NO3, so nitrite must be NO2 with the same charge, -1. Okay, well, I have a +3 and a -1. So if I start with the +3 from the iron, I have to do 1 nitrite, 2 nitrites, 3 nitrites. There's your iron. There's your nitrite. That gets you your neutral compound. So I have to have 3 of the nitrites to the 1 iron. So 3 -1s to neutralize the +3. So that's going to be my iron. Again, I need parentheses. I put my nitrite inside the parentheses, and I put the subscript 3. That way I have 3 of the nitrites. Okay, let's do ammonium sulfide. The cation can also take on the, the subscript. So ammonium, that's a +1. Sulfide, well, I look at the periodic table, and sulfide is a a chalcogen, it's group 16. So if you start counting back, like if you do your negative numbers counting backwards, group 17 is a -1. Group 16, the oxygen group, is a -2. And so sulfur has a -2 charge. All right, well, that means I'm going to need, so there's one ammonium plus an ammonium minus the sulfide. That gives me a neutral charge. Okay, so I need two of the ammoniums to neutralize the one sulfide. So that means now ammonium is going to have to go in the parentheses, NH4S. That's your ammonium sulfide. Oops, that's, I forgot something. I need two of those. There we go. And then of course, potassium carbonate. So this one kind of goes a little bit backwards. So if we remember, potassium is in group 1, so it's a +1 charge. And then carbonate, when we remember what it is, we either find it, we remember what it is, it's a CO3, 2 minus. Okay, so the potassium is a +1. The carbonate is a -2. So I'm going to have potassium plus potassium, oops, plus the carbonate. That'll give me 0. KCO3. So I need two of the potassiums for the one to neutralize the one carbonate. Well, this time I do K2 CO3. I only put, if I use parentheses, it's only for polyatomic ions. This time the potassium ion was there on its own. I don't need a parentheses around potassium for the subscript. So if it's an ion that comes from the periodic table, you don't use parentheses. We can also have compounds made only of polyatomic ions. Well, then you have to figure out where they split. Now I see my ammonium ion, and then I see that ion there, which I would learn that second ion. That shows up a lot on exams, standardized exams. People who write exams seem to love it. But let's think about this. So ammonium is it's a +1. C2H3O2 has a -1 charge. That's your acetate ion. Now we notice that it goes together +1 -1, which helps. So we know that the name of this, let's see, ammonium. So the name of this, ammonium acetate. So you're still doing this the same way you were doing before. Cation first, and then your anion when you're naming. It's just you have two polyatomics making the molecule this time. So here's one, ammonium phosphate. Okay, well, how do we do this? Again, our ammonium is a +1, but this time phosphate is a 3 minus. Okay, so I'm going to need ammonium plus ammonium plus ammonium plus the phosphate to get neutral. So that means I need 3 of my ammoniums to the 1 phosphate. Okay, so since I have 3 ammoniums, the ammonium is gonna go in parentheses, and I get 3 of those, and then I only have the 1 phosphate. So that is the formula for ammonium phosphate. Another thing that you're going to want to pay attention to when naming is that your polyatomic ions can have hydrogens added to them. And so every time you add a hydrogen, your ion becomes more positive by 1. And then the name will change slightly. So if you look here at the phosphate, you see you start with your phosphate at a -3. I add one hydrogen, it goes from a -3 to a -2. I add a second hydrogen, it goes from a -2 to a -1. And I stop there because if I add one more hydrogen, it'll produce a neutral compound that's not an ion. So if it's neutral, it's not an ion. If I go H3PO4, I have an acid. So I can only add hydrogens until I'm up to a -1, and then I have to stop for the ions. We'll talk about acids in a minute. So, but the way this goes is your phosphate. When you add one hydrogen, you can either name that hydrogen phosphate. An older way to name these is you would also call this like biphosphate. And for all of your polyatomic ions, your bi prefix only works for one hydrogen added. Otherwise, you dihydrogen phosphate when you're up to two hydrogens. Again, sulfate as a -2, add one hydrogen, goes up to a -1. Sulfate, I add a hydrogen, I'm at a -1. I can't add any more hydrogens or I get an acid. And that's going to be hydrogen sulfate or bisulfate because it has the one hydrogen on it. So the charge does not dictate when you use the bi prefix. It's the one hydrogen. But if you just want to stick to like hydrogen phosphate, hydrogen sulfate, that's fine too. But just know that can happen, and make sure you're also getting used to used to these ions because a very popular one used baking soda is sodium bicarbonate. So carbonate is CO3 2 minus. So your bicarbonate or your hydrogen carbonate would be H CO3 with a 1 minus. Sodium is a plus. Your sodium bicarbonate would be sodium HCO3 because your bicarbonate or your hydrogen carbonate is its own ion. Okay, so now we're up to covalent compounds. When you see a covalent, you should be happy because these are actually pretty straightforward to name. So again, binary made of two different elements. Covalent, these are where bonds are formed by sharing electrons. We talked about that a little bit earlier, versus the ionic compounds that are held together by electrostatic forces. Always keep in mind covalent bonding happens between atoms that are non-metals. So if you go to the periodic table, it has to be like carbon and hydrogen, nitrogen and oxygen, carbon and oxygen. It has to be two non-metal atoms because if you go with a metal and a non-metal, you get an ionic compound. Or you have an ionic compound if you have a polyatomic ion. Now, let's review again for a minute. In ionic compounds, we only use the names of the ions. So you see here I have one magnesium and two chlorides, and I only call that magnesium chloride. And you remember I needed the two chlorides because a magnesium is a 2 plus, a chloride is a -1, and so I needed the two chlorides to neutralize the magnesium. And so I just named this magnesium chloride because we have to put ions together in the proper ratios to make sure we get a neutral compound. It's not the same way with covalent compounds. So with covalent compounds, you're going to start using numerical prefixes based off the subscript. So di, tri, tetra, penta, hexa, hepta, octa, nona, deca, and that's 2 through 10. Make sure you start learning these prefixes. So here, for example, you see NO, and this is a special prefix here. So this one is called nitrogen monoxide. So mono is the prefix for one, but you notice that here I have oxide, then I have mon. I dropped that O off mono because the atom that I was putting the prefix on starts with a vowel. So if the atom you're putting the prefix on starts with a consonant, you leave it mono. If the atom you're putting the mono prefix on starts, for any of these, the atom you're putting the prefix on starts with a vowel, you drop the vowel at the end. So So let's say you had O4, something O4, okay? Well, that would be tetra. Tetra is 4. However, oxygen starts with a vowel, so this would be tetroxide, not necessarily tetraoxide. There are, I wouldn't necessarily count it wrong, but you also want to make sure you're thinking about standardized exams. Standardized exams would not put tetraoxide, they would put tetroxide. And that sounded very similar, but you get the point. The mono prefix we're not going to use a whole lot though. So if you look down here, you have Si6. Okay, well, sulfur is nonmetal, iodine is nonmetal. So this has to be a covalent compound. So when I name it, I get sulfur and then hex iodide. So yeah, I is I. So I minus. Well, no, we're not doing that. Let's just, we'll do oxidation states at another time. But so you have your I6. So that's sulfur hexoxide, not hex iodide. I'm not using oxide. Yeah, switch my brain over. Uh, not hexa iodide because iodide starts with a vowel. So I just dropped that A off the end of hexa. Something else you're going to want to start working on are common names. You're definitely going to want to know your list of alkanes here. The ones that are the hardest are methane, ethane, propane, butane, because their numerical prefixes don't match what you would think. So like here you see penta, 5 carbons, hexa, 6 carbons, hepta, 7, octa, 9, nona, 10, deca, nona, 9, deca, 10. Those make sense as far as numerical prefixes go. But your meth, eth, prop, and bute, those don't really follow the prefixes you've been getting used to. So I would really focus on learning these first 4. Make sure you know your methane, ethane, propane, butane is 1, 2, 3, 4 carbons uh, sequentially, along with names you might find for other compounds. Remember, your NH3 is ammonia. Uh, I guess you could call it nitrogen trihydride. Your C6H6, that's benzene, that's a common name. CH2O, that's formaldehyde. You wouldn't call that carbon dihydride oxide. You just wouldn't name it that way. It's formaldehyde. There are IUPAC names ways of naming it, but that's not something you'll do till later on, like in a higher level of chemistry. CHCl3, that's chloroform. So, like for example, the IUPAC way of dealing with that would be calling that trichloromethane, but the common name is chloroform. And N2O, so you could call that dinitrogen oxide because you're dinitrogen, you have 2 nitrogens, but its common name is nitrous oxide. So I think the best way to really get into covalent compounds is really just to start naming some. We'll do some formulas and we'll do some naming. So SF6. So you noticed how the naming is still like it was with the ions. We have the name of the first atom, and then the second atom is going to take on the IDE ending. Later on, you'll find out that the second atom does take on negative character, but that's something for down the road. You just want to do the name of your first atom. Your second atom will take the IDE ending. So here, SF6, so we have sulfur, and there's 6 fluorines. And so that's going to be hexa. This time I'm leaving the hexa on because my atom starts with a consonant. Sulfur, hexafluoride. Oh, so the next one, ethane. That's a common name. That's one of my alkanes. And that's right here. So you're going to want to make sure you can identify these based off common names. So that's C2H6. You will see those on exams. CO2. Okay. Carbon. No prefix because there's just one of them. 2 oxygens. Dioxide. The next one, CO, carbon. This is a case where you use the mono prefix because again, your mono prefix is typically going to be for the second atom in the compound. So here we have CO, so carbon monoxide. I don't put the full mono prefix because oxide starts with a vowel. Here's another common name, ammonia. I should know that that is NH3. Here we go, dinitrogen pentoxide. Okay, well, really what I do is I'm going to put down exactly what it tells me. Dinitrogen, 2, so di is 2, penta is 5, so dinitrogen in 2, pentaoxide, O5. Let's see, S2F2. Okay, well, I have 2 sulfurs and 2 fluorines, so disulfur. Penta, oh, what am I doing? That's 5, penta's 5. So disulfur, difluoride, 2 fluorines. And so then we will end with CF4, so 1 carbon, so carbon. 4 fluorines. The prefix for 4 is tetra. I use the whole prefix because fluoride starts with an F. Carbon tetrafluoride. So again, your covalent compounds should be pretty straightforward naming. All right, we'll finish up this chapter with acids. So acids are molecules that we'll use this definition for now. This is going to be your primary definition of an acid. When you put them in solution, they're going to leave protons in solution. Okay. Now, keep in mind in chemistry, we use a proton we designate as H plus. You'll see that in chemical equations. However, this does not actually exist in solution. What's going to happen is your acid is going to break off a hydrogen. That hydrogen will collide with the water and it will form hydronium ions in solution. Now, the reason that protons are not in solution, so your H pluses are not in solution. So this is something to think about because what is an H plus? So if we think this, well, this will be, we'll get deeper into this a few chapters down, but I want you to realize what an H plus actually is. So hydrogen, if we look at the Lewis diagram, have 1 proton. If I strip that proton off, electron, oh my God. I'm having one of those days where I can't get my words right. They have 1 electron. If I strip that off, I get my H plus. But the nucleus of a hydrogen is just a proton. So what we originally had was a P plus with an electron orbiting around. So my H plus is my proton nucleus without its electron. So it's just a proton. So a proton by itself can't be an ion. This is no longer an ion, it's particle radiation. So your H plus, we will use it in chemistry, we'll use it in chemical equations, but know that in reality they exist in their hydronium format. So the first group of acids we're going to be looking at, you'll notice they all have a hydrogen and an anion. And so when your anion is not an oxoanion, what the name of your acid is going to take a hydro prefix and an IC ending. And the IC, the hydro and IC will go on the root of your anion. So for example, in HF, your anion is fluoride. So the root of that is your FLUOR. Okay. And so the fluoride is not an oxoanion. So this has to be hydrofluoric acid. Again, cyanide is one of your polyatomic ions, but it's not an oxoanion. So you have hydrocyanic acid because the CYAN, that is the root of cyanide. Your HCl becomes hydrochloric acid because the fluoride is your anion. Hydrosulfuric acid because sulfide is your anion. So hydro and then your IC. And then hydroiodic because iodide is your anion. So again, these acids where you don't have, where your anion is not an oxoanion, your acid will take the name beginning with hydro, base of your anion, and then an IC ending. Okay. So let's see but what else could we do? HBr. That's hydrobromic acid. So start to get the hang of that. And then of course, how do you deal with the acids made from oxoanions? You're going to use, so what you're going to be thinking about is any oxoanion that ends in an ATE will get an ending of IC as its acid name. Any oxoanion that ends in ITE will get OUS as its acid name. And then I want to find one and show you that you still use the entire uh, oxoanion family name. Okay, I can do that one. So if we look here, your NO3 is nitrate. So when I put that hydrogen on there, it becomes nitric acid. And again, start going through these and look at how many hydrogens are on here. Do you see how nitrate has is a -1? It can only hold one proton. You see how sulfate is a -2? It can hold a maximum of 2 protons. But it's sulfate, it becomes sulfuric acid. Phosphate is a -3. It can hold a maximum of 3 protons. Because remember, every proton is a +1. And so every time you put that on there, it's going to go from -3 to -2 to -1 and then to H3PO3, which is neutral. But here, this is phosphite. So this is going to become phosphorus acid. So here we have, well, that should have a minus there. The acetate ion, it's a -1, so it can hold a maximum of 1 proton. Acetate, ATE, becomes acetic acid. Let's see. Here we have bromite, -1, max of 1 proton. ITE becomes bromous acid. And here we have sulfite, again, a -2, maximum of 2 protons. Sulfite becomes sulfurous acid. Let's see, I want to take, let's see, where's my chlorate family? Okay, just to kind of give you an idea of that the whole oxoanion family name comes through to the acid. Let's make an acid out of ClO4, and that's a -1. So that's perchlorate. So it has a -1, so it can take a maximum of 1 proton, HClO4. And so the ATE becomes IC. This is per, so I still bring down this prefix, per chlor. I get the base of the word. ic acid, perchloric acid. Let's see. What about BRO with a -1? This is hypobromite. And you notice I have hypo as a prefix, ITE as an ending. ITE becomes OUS. Hypo stays on there. So, and it's a -1, so it can take a max of 1 proton. So HBRO makes it neutral. And I keep the hypo prefix. And I add the OUS ending for the ITE, and it becomes hypobromous acid. So this is how your oxoanion acids will work. Make sure you're reviewing your acids that have anions that are not oxoanions. And this gets us through our beginning of naming. So you're going to be using this naming a lot. I would start practicing with it. Your next assignment's going to have a good number of these, but naming is going to be very core to your chemistry education all the way through. So again, get that list of polyatomic ions, really start learning it. I have it kind of color coded. The first section is going to be in kind of an indigo color, and those are going to be the polyatomic ions you will see most commonly. I gave you a good list on there, showed you some of your anions with hydrogens added, showed you how your oxoanion families work, but just compare the polyatomic ion list I put on Canvas to what we're doing here in class. And that is going to end chapter 2. So tomorrow we will begin chapter 3. All righty, thank you.